So this is my demo presentation for the scalable compliant module I've designed. Here's the introduction. So these were the project aims. I basically wanted to design a module that you can implement to any pre-existing rotational drive system that would add compliance. So compliance is the opposite of stiffness. So what you're essentially looking at is a rotary suspension system, or at least that's how I viewed the project in the early stages. So after the progress demo, there were three further aims that were set by my supervisor, which we'll address later. So here's the central unit. This forms the basis of the system, with the inclusion of the case. The ball bearings are loose so that they can reduce the friction the unit experiences when rotating inside of the case. The case is used to minimize any sort of torsional force or stress on the axle. So this is it inside the case, implemented to the non-back drivable motor. You can see there, and again, the resonances that are caused by the oscillation of the energy from kinetic energy to spring potential energy. So now we come on to the mechanical aspects of the design. So this was the manufactured system I tested. The belt on the left is tensioned with the cable, and the encoder on the right is stuck on with electrical tape, which isn't really a problem because this isn't a manufacturing project, this is a proof of concept project. So this comes to the CAD model. Half the case in this image is hidden, so that rotary encoder holder isn't actually floating in midair, but it allows you to see the model that I made on CAD and perform simulations on. I defined all the joints, so this degree of freedom view actually explains quite succinctly how the system works. So on the left, you can see it's fixed because it's attached to the non-back drivable motor. On the right, a rotational force is applied, and you can see that the springs absorb that energy and allow the axle on the left-hand side that is fixed to not experience any of that rotational force. So here I'm just driving it to plus 18 degrees and back to 0. Now I'm holding it at 0 and it can still drive. It stores that energy from the motor, and it does not force my hand out of the way. So this is the sectional view from the computer aided design. So here you can see the different components. Just quickly go through them. So you can see the magnets here and the copper plates here, which is used for the eddy current damping, which gets rid of the resonances. Here you can see the ball bearings and the zip ties and the zip tie cozies. This is what connects here to the motor. This is the case to motor connecting unit. This here and over here, they're the GT2 timing pulleys, and you can just see in here that yellow component there, which is the thrust bearing. Let's get rid of that. Okay. So I did some finite element analysis for a maximal condition. So for this specific unit, that would be 12 springs. I'd previously calculated the spring constant for these springs. So I exerted the maximum force, the maximum extension, force related to their extension on both these plates. And this is an exaggerated scale here, so the maximum displacement is actually only 0.07788 millimeters, even though it looks a lot larger than that. And what's also important to note is this was actually an earlier prototype I performed the FEA on, where I was planning on using 22 ball bearings. I later reduced that down to 10, so the final component I'm using in this system is actually stronger. Either way, this FEA proved that the component was more than strong enough, so another finite element analysis wasn't carried out. So I ran a simulation to predict what the torque angular displacement characteristic would be, and I did this using MATLAB to generate data, and that data was generated by essentially finding the spring extension, which I could times by the spring constant and therefore give a force. But to get the spring extension, I had to get out my total stress length. So it would be the total stress length minus the pre-stress length, and I would calculate the total stress length by calculating the Euclidean distance between essentially the plates, which is the pre-stress length of the spring, and the distance between the origin, which is on plate 1 is set at the origin, but that's also where plate 2 begins on those two axes. And then as you rotate plate 2 around, I calculate the Euclidean distance from the x and y distances to find the total distance in that direction. So then I can find the Euclidean distance between that offset and the pre-stress length to give me the total stress length. So talking through the results here, it looks like the characteristic is non-linear, which is desirable because it allows for agonist-antagonist control. But what's important to note in this table, so this is all relative to the percentage of force at 30 degrees, so it takes out of the equation the springs and it's purely mapping the rotational nature of the relationship. But what's interesting about this is that for my system, I found that the angle of about 7 degrees was equal to the static frictional force you'd have to overcome. So everything under about 7 degrees is muddied by that static frictional force. So here's the actual testing I did on the unit. So you can see I basically suspended a water bottle and added water to increase the mass suspended off this pulley. And I would measure the rotation with the encoders. And so here it was found that a force, static frictional force for this system found to be larger than force required for rotation under about 7 degrees from testing, or about 6% of the total force required for the 30-degree rotation from the simulation. And so we're going to see a video in a minute where we talk about how there's this lag because of the frictional force. I'll show you that now. So here again, I'm driving it to plus 18 and minus 18, but I'm using the Arduino plot function. Oh, sorry, plus 18 and 0, but I'm using the Arduino plot function. And you can see here, the motor goes to plus 18 and the output encoder goes to about, what is that, 12? Stops about that sort of 12, 13, low teens mark. Before, when there's a change in direction, then the static frictional force is overcome. And so it shoots back up and then comes back down. Okay, so now onto the electrical aspects. So the plan was to use eddy current damping to remove those resonances we saw earlier. That's sort of the sort of stuttering sounds that you could hear in that video. So the idea behind the eddy current damping was that you could it would be passive, it wouldn't require a power supply, and you could very easily calibrate it by adding or removing magnets to increase the strength of the magnetic field. And all that you need to do is affix these copper plates to the rotational aspect of the system, and the magnets to the stationary plate on the output shaft, which is simply used to stop the axle from sort of twisting anyway. But it's just this adds functionality to the same plate. So it was found that actually the eddy current damping in this system wasn't being used because the static frictional force coefficient was so high when the case was on that it would take out a lot of the energy from the system as it were. So this oscillation between potential to kinetic energy was basically non-existent. And I know it was friction with the case because you could see when the when only half the case was in place, that you would get noise and air resistance, but you would still have this resonance effect. But as soon as the case is closed, then you don't have the resonance effect, and I can only imagine the difference being the increased frictional force. So here is the lack of resonance in the manufactured system. So the plot is blank at the moment. I force the arm to store up energy. I let it go. And we can see there's no resonance there. It just goes up and it doesn't quite return fully, which suggests a lot of energy has been taken out. And here I give it a larger force, and so you can see it goes all the way up and then still doesn't return fully because energy is being lost from the system through heat, noise and air resistance. So then the final electrical aspect is the wiring. There's a picture of the wiring. I'll just read through the points. So it's controlled with an Arduino Mega clone and an L298N H bridge. The Arduino is on a 5 volt. The Arduino's 5 volt supply is used for the H bridge and encoder logic signals. The Arduino ground and the power supply's ground are connected to create a common ground. The power supply to the H bridge, which is what's used to drive the motor, is limited to 15 volts and 2 amps. So that's done by short-circuiting the power supply, so providing it with minimal resistance and then manually limiting the current knob, driving the current down to 2 amps so it can't go above that. So then the H bridge enable pin, which is used for PWM, is just jumped. So it's always maximum at 100% intensity. The encoder signaling wires connected to the Arduino, the encoder signaling wires are connected to the Arduino on interrupt capable pins for maximum responsiveness. I'll talk about that more in my code demo. So the encoder shield wires are connected to common ground at the end where they're exposed. I'm not sure what they're connected to at the actual encoder end. And then the signaling wires defines encode in such a way so that an equal rotation on both shafts provides a rotation of the same sign being registered. So that takes me on to the software aspects. So these are the two main bits of relevant code, I think. So I've got the main loop and then I've got the functionality I use to actually drive the motor. So the main loop, what I'm doing here is I'm defining and I'm defining and setting up the pins, serials and variable. I then check the serial data. This is the beginning of the loop. I check the serial data. If there's data, I decode it and save it as a new target and move on to the next step. If there's no data, I just move on to the next step. I read the encoders and update position variables. If it's changed, I'll print that to the serial. If it hasn't changed, I'll go straight to the next step, which is to calculate the angle between the current position and the target, and then to use the PID algorithm to calculate what angle to drive the motor. And then I send that to the motor driving function. So then you can see the motor driving function, there's one function for each direction, and all that does is it takes the angle that's being sent to it, saves the current angle, turns on the motor in the correct direction, and then it sets up a while loop, so it just checks, it just updates its position information until the condition is met, which is basically that the starting angle has changed by the amount you want to drive it. And then once it has, it turns off the motor and returns to the main. So that's explained here. So the first thing that I do in my script is I include the library encoder.h, which you can see here. And all that does is it essentially simplifies the interrupt functionality for the Arduino Mega board that I would have to write. And I think it's important to note that both of the encoder pins are connected to interrupt capable pins. For best performance, so they never miss a pulse count. And there are 2,400 pulses in 360 degrees, which means 1 degree has about 6.67 pulses. So I define my pins, as you can see, so I'm using the encoder class, which is included in the library. I define my motor pins as well. Then I move on to the setup. So I'm setting up here my serial. and I'm printing this message to the serial, which basically gives the user instructions on how to use it, what sort of values you can enter, and importantly, the range of the motor. Because of the clamps on the motor, if you go outside of the range, then essentially the clamps pull apart and the belt flies off. Yeah, and then I move on to defining my motor state, which obviously I'm going to start with the motor being off to avoid it just driving every time I turn it on. And then I initialize my variables. So I've got my encoder variables here. I've got my main loop variables here. So angle target is what I'm storing the serial, well, the processed serial data into. Drive is the variable that I'm using as the amount I want to move each motor by an angle. So it's an angle I want to move each motor by in either direction. And then I've got my gain PID values, and I've initialized, I've got my gain values and I've initialized my PID variables. So we come into the loop. The first thing I do is I check if there's something available in the serial. If there is, I decode it. So what I'm doing here is quite straightforward. I'm just in a while loop until I hit a new line or a carriage return, and I'm just scanning for a sign. If there's a negative, fundamentally, it's basically just a negative sign. If there's a negative sign, then I update the sign flag to -1. And then any other character, I'm just saving to a new string. I convert that new string here into an integer, which I check is within the range of ±80. And then I apply the sign flag. So if the sign flag is changed to -1, then we have like -80, for instance. It'll print a warning if something goes wrong, and it prints out a confirmation of the value you've entered. So next is the encoder. I update the encoder position. I read the encoder, and if it's changed, then I print to the serial the new values. So the serial communication is showing you, rather than on every loop, it's only showing you when there's a change of position, which is quite nice. And then I go on to the PID functionality. So that's fairly straightforward, I think. Essentially, you've got your prior error, which is storing the error from the error from the previous loop before you've updated anything. And you calculate your error by just finding the difference between the target and the output shaft angle. And then your derivative is essentially a scaled difference between your two errors, your previous and your current error, because sampling times are constant. So that means your integral error is essentially a scaled summation of all of your errors. And then to calculate the drive angle, because we don't want to drive it all the way, we want to drive it in sort of controlled steps. So we're just taking the error and then scaling that by the potential gain, and then we're adding on the scaled integral error and the scaled derivative error. And so the drive can be between, it can be between, in theory, +80 or -80. So our drive here is basically being sent to the appropriate clockwise or anti-clockwise motor driving function, depending on its sign. And so, well, they're essentially the same function, the only difference being that the pin definitions are reversed. So that's low-high, this is high-low. But again, the functionality for this is very straightforward. I'm just saving, when you enter the function, so you're passing the function the amount you want to drive it by, essentially in degrees. So you're saving the starting position, you're turning on the motor, and then you're just looping an update that just updates the position and angle information. And you're just saying, I will stop the motor. So the terminating condition of this loop is that the angle of the motor reaches the starting angle plus the drive angle. And that's, and then I turn off the motor and I return to where I was in the main code. And that's the entire script. Yeah. Okay, so now that takes me on to the video demonstration of the working project. Okay, and then this will be a video of when the system was somewhat broken but still usable. So you can see here the flange that secures the case to the motor connector has snapped off, so I've had to use wires instead. So there is significantly more free play throughout the system, which makes controlling it not as good. Definitely not as accurate. You can see the amount of free play here. You can actually see the case is rotating within the case holder due to the frictional forces. And this is not ideal. However, we press on. So I've set the motor up here. I'm just going to drive the motor to a few different angles across the range. I think I go from -70, and then I take steps to 0, and then up to about +70, and then I think I return it to 0, something along those lines. So here I'm driving it down. Oh. Driving it up maybe to 30 degrees. And that's the end.